Hi students, Mr. Epperson here with a quick video on electronegativity and bond types. And electronegativity is a word that we discovered last semester and discussed it quite a bit. And just to refresh how it works, I'll go over the definition briefly, but we're looking at the most electronegative elements over here on the right being the most red. The least electronegative elements kind of being over here in lighter yellow. And you'll notice the trend is left to right. It gets increasingly electronegative, and also from bottom to top. It gets increasingly electronegative as you go up in the periodic table, wherever you are, pretty much. There's a couple exceptions right here, but we don't really need to worry about the exceptions to the general rule, because mainly what we'll be dealing with is nonmetals, which are over here on the right side. The metals are on the left side of the periodic table. The nonmetals are on the right side of the periodic table. And nonmetals are very electronegative, and metals tend to be very low in their electronegativity value. So they aren't very electronegative. So what is electronegativity anyway? Just as a reminder, because we have discussed it before. It's a measurement of how attracted valence electrons are to the nucleus of an atom. So if we look at this atom here of fluorine, these are the valence electrons in the outer energy shell, what we call the valence electrons, yeah. And they are attracted to the nucleus. The shell on the inside has attraction as well, but because it's not involved in bonding, we really don't care about it much anymore. Just the fact that they're there is important for charge, but they don't really serve any purpose in bonding. So we talk always about this outer energy shell, the valence band, as it's also called. Okay, so that outer energy shell is where the attraction is that we're looking at for electronegativity. And the value that we give that is how intensely attracted that outer shell is to the atom itself. And we'll notice that it really matters how big this value is when the atom is bonded to something else. Because as you noticed with this table here, there's a lot of different values, and some of them are very similar and some of them are pretty different. So just to review where we've been, the connection and the way that electronegativity can be explained is, we've already talked about this last semester, so I'm just going to briefly go over it. Atomic size has a little bit to do with electronegativity. Remember that atoms have a size, so all these atoms here are, showing their relative size to one another, and it would make sense that the more protons that you put into an atom, the bigger it would get. But that's actually not the case. In general, it gets bigger as you go down. But as you go from left to right, it actually gets smaller. If you remember periods over here, listed 1, 2, I'm just writing over them here. The period tells you how many bands there are. Okay, 1, 2. Lithium has, and we just pretend this is the entire nucleus right here. That's not a band, okay? So that's one band, that's the other band, and the number of periods that are there tells you how many energy shells there are. And so this is the second energy shell, this is the first one, and all three of these examples here have 2 energy shells because they are in the second period, right? So here are the 3 examples. Every time I add a proton, I also add an electron. But when I add an electron to that outer band, I've now increased the attraction between the band, the collective attraction between the band and the protons in the middle. And the more that I increase the number of electrons in that band, the band is never going to increase. I'm not going to get another band, and it's not going to increase its distance, because the more I put in there, the more it's going to sort of contract its size. There's more positive charges in the nucleus, and so the negative charges on the outside are going to be drawn in as I put more electrons in there. They'll sort of collectively pull that radius in smaller and smaller, so that at the end I get this really, really tiny atomic nucleus. The reason this is important is the idea of an atomic size shrinking also goes with the idea of the electrons being held on tighter and tighter and tighter by the atom itself, by the protons in the nucleus. It's holding on to those electrons. And it's kind of very much like a fist. If you were to open your fist and close your fist, the smaller your fist, the smaller the atom, the tighter it's being held. And the weaker that hold, a very loosely held fist, is going to be bigger, but very loose strength on those electrons. And it's very similar to the analogy of electronegativity. So you'll notice that the trend, going back here, the trend is atomic size goes down, gets smaller, but electronegativity gets higher. The most electronegative atoms being in this group here. These noble gases, they do have a size, but they don't have an electronegativity value that we care about because they don't bond. Okay, they're non-bonding. So we don't care about the noble gases in group 8. So we really start caring about the atoms in 7a and to the left. So at least for reactions and things like that. Okay, so here's the big idea with bonding though. Okay, the atom with the higher electronegativity value is going to pull electrons towards it. And it says electron cloud. If you remember, we don't ever really know exactly where electrons are. Maybe you don't remember that, but that is a concept in physics and in chemistry, that we never really know where an electron is. We kind of have an idea, and we can use models to sort of get this idea of these bands and even predict further than that, but it's not a very good model to say at all that atoms have electrons floating around them in orbits like a solar system or something like that. That is not the way that they are constructed. It's better drawn as a cloud. And the cloud of electrons is sort of showing sort of this sea of where an electron could be, like a predictability cloud. Basically, that cloud is being pulled more towards the electronegative atom that's involved in the bond. The more electronegative an atom, the more it's going to pull those electrons towards it. So in this game of tug of war, the question is, what happens when you bond two atoms? Like, for instance, if I just pick two out of the hat, sodium and chloride, and I bond the two of them together, right? It's kind of what chemistry is. It's about taking two elements and smacking them together and making some kind of a bond with that, right? I see their electronegativities are very different, 3.16 and 9.93. And when I put those together, this atom right here, chlorine, is so electronegative, it's just going to rip that electron from the soul of sodium. It's just going to take that electron away. It won't have that electron anymore. And that's what's called the ionic bond, where it just rips the electron away. It doesn't care, and it just takes it. And then we learned a lot about ionic bonds last year. This is basically the rest of the lesson, is trying to figure out what type of bond is going to be made now that we know the electronegativity values. An ionic bond or a covalent bond, and you'll see there's two subcategories, polar covalent and nonpolar covalent. So we basically need to look at this map here, the periodic table map, with the electronegativity values and compare them to see what kind of bond are we going to get. Now, when we look at the different scale, the scale here, when we look at the different types of bonds, we'll see that there's a range, okay? Obviously, if they were the exact same electronegativity value, identical atoms, for instance, like if you were bonding hydrogen to hydrogen, which is what H2 is, there's going to be no polarity at all, meaning there's no concentration of that electron cloud on either atom. It's equally split. They both have the same desire for the electron as the other, because they are the same atom. But there's sort of this range of what we'd still consider nonpolar covalent bonds. By the way, just to get the polar word out of the way, if you think about like north and south poles on a magnet, for instance, that's a polar relationship where like a south pole will bond to a north pole, right? If you've ever played with magnets before, you know how this works. They bond together because they're opposite poles. Okay, in polarity for chemistry, we think about poles being, is there a concentration of electrons on one atom in a bond? And if so, then you're going to get a kind of a clumping of electrons on that atom, and that will develop a charge difference in a molecule. So I'll give you some examples of that in a moment, but that's the idea of the word polar there. So there's your range. These would be good to write down here. 0 to 0.5 is considered still nonpolar covalent. Polar covalent is basically anything from 0.5 to 2.1. And that range there is basically a covalent relationship where they're still sharing electrons like we've always said, but one of the atoms wants those electrons more. And so much more that they sort of pull that cloud over on top of it so that it develops this polarity. And then the last one is called an ionic bond, and that's anything greater than 2.1. So anything larger than 2.1 is going to be considered an ionic bond, and that's really how we define ionic bonds, is that the difference in electronegativity is so great that it's just basically going to, one atom is going to get all of its electrons pulled away from it, and the other is going to steal the electrons and develop the charge. So the reason that we'd always say metals and nonmetals are ionic bonds is because the ability to make a difference this big, anywhere from 2.1 and up, is it really only happens between metals and nonmetals. Any of these values basically have to happen between two nonmetals. Okay, here's the polarity idea I was talking about. In this case on the left, you have a nonpolar example of the electron cloud. This little like kind of bag here is representing where the electrons should be. Okay, when you have two identical atoms bonded together, you're going to have basically a completely nonpolar relationship. There's no side of this that has more charge than the other, more electrons than the other. Okay, this is nonpolar, but when you do have a big difference, like H and Cl have a very big difference in their electronegativities. Cl is far more electronegative than H. And when this happens, that bond is skewed towards the chlorine in terms of how many electrons are over by the chlorine atom. Okay? So because chlorine wants those electrons more, in a sense, than hydrogen, you have sort of this misshapen, kind of pear-shaped electron cloud. And you'll notice this funny little symbol here. This is the Greek letter delta, and it indicates a slight negative charge or a slight positive charge, depending where we're looking here, right? The way to draw this, by the way, is sort of like drawing the number 8, but you sort of stop before you complete the other side. I've always learned to draw it like that. I also see down here, the way the computer draws it is kind of like, I don't know, it almost looks like a Pokemon to me or something. This is the Greek letter delta though, and yeah, that's what we're drawing. When we put the positive or negative though, what we're saying is that when it's negative, that means that there's more electrons there. Remember, they have a negative charge. When it's positive, slightly positive, that means there's fewer electrons there because it's now has a slightly positive charge. Now, in an ionic bond, there is no polarity here either, because it's just the bonds have just been transferred. Sorry, the electrons have just been transferred from one atom to the other because of such a large electronegativity difference, and that's how they satisfy the octet rule and achieve stability. Okay, let's do some practice here. Can you figure out the type of bond that would exist between carbon and hydrogen? Okay, so first we're going to look for hydrogen, we're going to look for carbon, and we'll put their values next to each other. 255 minus 210 equals 45. And we go back to our little map earlier that we had, and we see that in this case, 0.45 is going to lie within the nonpolar covalent. So what type of a bond is this? Nonpolar covalent. And that's the way that you would draw the electron density. It's just equally shared between the two. Even though they have slight differences in polarity, we're not going to represent that here in the drawing. It's considered still nonpolar covalent. Okay, how about with H and F? You have 3.98 and 210. and you subtract them from each other, you get 1.88. What kind of a bond is that? 1.88 is going to be right about here, and that would be polar covalent. Okay, polar covalent. And here's the way that we would diagram that. Again, that sort of pear-shaped, or it looks like one of those funky dog toys. This is an electron-rich region over here, where the fluorine is, and an electron, what we'd say an electron poor region. Like there are fewer electrons here, and there's lots of electrons over here. They whiz around in sort of randomness, but because there's more attraction to this, you're going to find them more often on this side than you would find them over here. Okay. Now the last one, you might be able to predict what it's going to be. Sodium and chlorine. 3.16 minus 0.93, such a large difference between these two. 2.23, and no surprise here, 2.23 is right here in the ionic band, and it's clearly an ionic bond, okay? And the way that we'd represent that is not with any sort of electron cloud, because really you're just, the electron is jumping from one atom to the other. So that's the way that we would represent polar bonds and how those come about. And I hope that was helpful for understanding electronegativity.